All right, let's get started, everyone. So today's topic is going to be multilingual natural language processing. We'll spend a bit of time talking about transfer learning in multilingual scenarios and zero-shot learning. So if you only have data for your task in language X and you want to use it for the same task on language Y, how can you do that without having any labeled data in language Y? So this is very cool recent work on extending a lot of the resources that we have for high resource languages like English to solve tasks in much lower resource languages. We'll also look at translation, some recent advances in translation where you have a single model that can translate between like 100 different languages, which is something new compared to what we've been seeing so far, where you have a data set for French to English, you train your model, it can only do French to English translation, it can't do like French to German translation, right? So you might want one model to do all of these different directions. So that's the topic for today. Before we get started, the questions from last class were mainly about the midterm. How do you study? What do you study? And so on. So yes, there are practice midterms in the Piazza. Like I mentioned before, you should spend most of your time on the most recent practice midterm. Someone asked, the readings from last semester are different than the ones from this semester. So do they have to study all the stuff from the fall 2020 class? The answer is no. You should, all of the exam questions will be based on things that we've covered in these lectures and the readings for this class. So you should focus on that. If you've taken the time to look through some of those exams, you will notice that the questions are, they're designed to be hard to Google, obviously. So they require a lot of conceptual understanding, and there's not any like memorization tested, obviously, because you could just Google it. So yeah, so the class before the midterm, we'll have a review session where in the class where you can ask any questions about it. If you want a problem done from the midterm, or you want to go over some of the quiz answers or whatever, we can do that during that session. There's also a similar review session from fall 2020 that's on YouTube. So if you wanted to get some more feedback about random questions, then perhaps they're answered in that video already. So I'll put a link to that video whenever I update my syllabus next. Okay, so there have been a lot of requests to go over the existing quizzes that you guys have had. So I will try to do that at the end of this class. If we don't get to it, then I'll go over it next week. So we'll have some review next week. All right, any logistics questions? Okay. So today we're going to shift from basically English-centric tasks that we've been talking about for most of the semester to multilingual tasks. So for example, BERT, right? It was fine-tuned on strictly English data. Elmo, T5, all of these things. In fact, the only model that we've seen that has been trained on multilingual text is the byte T5, right? And there are various advantages of having that kind of byte-level tokenization for a multilingual data set, right? Characters can be shared across languages. That model is more robust to various types of noise and code switching and stuff like that. So, but we haven't gone into too much detail about these different variants. So how do you go about, if you wanted to apply our transfer learning, our pre-train and fine-tune paradigm to a different language, how do you go about doing that? So when BERT came out, there were a lot of attempts to just replicate BERT in different languages. So you get things like Flaubert or Faubert, which are specialized to a particular language, right? And so this basically involves taking the same BERT architecture, but pre-training it on text that has been collected in a different language, like French or Vietnamese. So this approach is fine if you can get enough text in that language, but it's kind of limited, right? Because your flow BERT model can only do French, your normal BERT model can only do English, and every time you want to add a new language, you have to go train a new BERT, which is obviously very expensive. Like none of you can even train a BERT on your Colab resources, right? So it's hard to scale this kind of thing. Although, if you are a engineer at a French NLP company, maybe you only care about French, and so you can use this model, and that's fine for all of your tasks. But in general, it would be nice if we had just a single model that could work for a bunch of different languages. So an alternate line of work has been to pre-train these kind of large transformer models on a mixture, a text that comes from a mixture of different languages. So there have been a lot of these kinds of approaches. MBERT, I think, was done by the original BERT authors, where they just included all of the different language Wikipedias in their pre-training data. So they had like 100 languages. There have been many approaches since then. We saw, for example, Byte T5. In this lecture, we'll look at a lot of results from MT5, which is literally the same exact thing as T5. The only thing that changed is the data. So we'll look at some of the data stuff as well. But the advantage of this kind of approach is not only that you just have one model for all of these languages, but also, for example, if I have a language where it's hard for me to get a huge volume of text, right? We know that GPT-3 was trained on hundreds of billions of words. It's very hard to get that kind of data in a non-English language, right? So is there a way for us to take advantage of all that huge data that we have in English and transfer some of that knowledge into our model that's actually operating on another language, right? So maybe we won't be able to transfer low-level things like syntax and other, the character script might be different, but at a higher level, right, the same kinds of concepts and events and whatever will be talked about in multiple languages, right? And so it intuitively seems clear that we should be able to transfer knowledge from one language that has higher resources to another one that has lower resources. So that's kind of the main advantage of having one model that can understand and produce all of these different languages. Okay, so the MT5 model, as I mentioned, is just the same T5 model that we talked about, except it is trained on this MC4 data set. So this is a common crawl, but if you think about the common crawl's usage in previous models that we've seen, for example, in GPT-3, they specifically used a language identification tool to characterize the data that they had. And they included some amount of non-English data, but it was a very small percentage of the data set. So this MC4 data is explicitly built to incorporate as much data from a bunch of different languages as possible. So you probably can't see this, but this is a distribution of like what percentage of the data set is in a particular language. So the most common one, of course, is English. Down here, then we have Russian, Spanish, German, French, Italian, PT. Any thoughts? What is Portuguese? Yes. Okay. All the way down to okay. What is just okay. Anyway, like low resource languages, right? So. This is on a log scale again. Some of these languages have very small number of tokens compared to English, which is obviously the biggest by far. So here are a comparison of some of the multilingual pre-trained models that have been released in terms of both the size and the number of languages. So MBERT was kind of the first one. It was just the BERT authors thought it would be straightforward to just release the same model except pre-trained on different Wikipedias. You can see it's very small, relatively, 180 million parameters, has 104 languages, but the data comes from Wikipedia, and Wikipedia is not balanced across languages. The English Wikipedia it kind of looks like this graph. It has way more data than any Indian language, for example. And Wikipedia, the number of articles and so on, does not correspond to the number of speakers of that language. So, a lot of Indian languages have a huge number of speakers, yet they're underrepresented on Wikipedia. Consequently, they're underrepresented in the training set of this MBERT model as well. So you can see over the years, years meaning like 2 years essentially, there have been a couple other attempts. So XLM, I think this line of work is by Facebook. They had some bigger models. Then eventually we moved from Wikipedia to the Common Crawl, which has a much bigger sample of data from different languages than Wikipedia does. And this table is taken from an MT5 paper, that's why it says ours. But MT5, of course, is a generation model, right? A sequence-to-sequence encoder-decoder model. And its data comes completely from the Common Crawl. So yeah, at this point, if you're interested in getting a lot of data for any particular language, the Common Crawl is probably the best bet to get that data at scale. On the other hand, it's very unclear what is in the Common Crawl. Like, there's a lot of random web pages. The content is hard to, characterize. I think there have been some attempts recently to try and do an analysis of what exactly is in the Common Crawl, because it's not like Wikipedia, is relatively well structured. There will only be an article about something if it's worth having an article about, as defined by, some moderator. In the Common Crawl, they're like crawling the internet. So anything that someone thinks is okay to put on the internet, which is basically anything, could be in this data set. So lots of potential issues with the bias of these models after they've been trained can be traced back to the source of data, which in this case is kind of unclear what is in this data set. So always something to be concerned about if you're just blindly trying to get as much text as possible to train your model. You should also be conscious of what actually is in the data that you're getting. Okay, so one of the coolest applications of these models that have been trained on multilingual text is the potential for zero-shot learning. So if I'm given some task, let's say sentiment analysis, and I have only labeled data for this task in, say, English, but I want to make my model work at test time on Portuguese, let's say. So I have no Portuguese sentiment data, labeled data, so I can't just take my MT5 model and fine-tune it on Portuguese reviews, right? Let's say that doesn't exist. So is there a way that I can still use my model and somehow just have it work in this other language without requiring labeled data in that language? So the idea is that if you have labeled data in, say, some other language like English, perhaps you can somehow repurpose these models to solve the task in Portuguese, even if you haven't seen that. So that this is the zero-shot setting. You don't have labeled data in Portuguese, but you want to solve the task in Portuguese. However, these settings usually assume that you at least have some text in the language that you want to do the task in. So in our example, I would want to have a lot of just arbitrary text in Portuguese. This is important for the pre-training process, right? If I'm using one of these models, I would hope that one of them has seen Portuguese before, so the model at least has some idea of Portuguese syntax and semantics, common patterns, and so on. Okay, so we'll look at two benchmark data sets that allow us to test the model's ability to perform this kind of zero-shot learning. The first is XNLI. So this is a cross-lingual textual entailment data set. Here are some examples from the data set. You can see that it has English. So here you have two sentences. You don't have to stay here and you can leave. And this task is a three-way classification problem. So you have to say if the second sentence entails the first one, or if it contradicts the first one, or if they have a neutral relationship. The interesting thing about, so So this kind of data is available in many English datasets like MNLI and SNLI and so on. There's so many entailment datasets in English. The interesting thing about this dataset is that it has these pairs of sentences and labels in a bunch of different languages, so French, Spanish, German, Swahili, Russian, and Chinese. And so you can really test a model's ability to do this zero-shot transfer by simulating this condition. So for example, I can train my model only on the English subset of this data set, and then at test time, I can switch to using Swahili text and see if the model is able to perform the task. So this is a common benchmark that people use for this zero-shot transfer. So one very common setting is exactly what I described, because English is usually the highest resource language. We're going to fine-tune our model on the English labeled data. So that would be all of these kinds of pairs in English with the corresponding labels. So the setup is I have my MBERT or MT5 model. It's been pre-trained on these 100 different languages from Wikipedia or the Common Crawl. And now I'm trying to solve this entailment task. So to solve this entailment task, I'm going to fine-tune my MBERT or MT5 model on just the English subset of this XNLI data set. And then at test time, I'm just going to feed in the examples from a different language. So even though the model has only seen English during the fine-tuning phase, it's seen all of these other languages during the pre-training phase. So the idea is that maybe it will just learn how to do the task, and that knowledge will transfer regardless of what language it is. And this actually happens to some degree. So this table is from the MT5 paper. If you look at this XNLI column, you can see that MBERT, if you do this, gets 65% accuracy. So it's like better than random, but it's not great. There have been many different multilingual models proposed. You can see that at the end, this MT5XXL model, so this is the biggest version of T5, which has 11 billion parameters, is actually doing really well on this task, which implies that it has learned a lot of knowledge about these other languages during pre-training, and the fine-tuning phase is basically telling the model what task to solve, and the model has learned that, but it hasn't over-specialized to only be able to solve the task in English, which is pretty cool. Okay. So one question that you might have at this point is, if I have some benchmark like this, one alternate way to solve this problem, let's say I have only English entailment data and I want to solve the entailment task in German. One way to do this would be to take Google Translate and translate all of my English data into German, and then just fine-tune the model on this translated data, right? Or I could fine-tune my model on the concatenation of my English labeled data and the translated German data. So of course this isn't like perfect German, right? But you now have a dependence on this external translation model. But it seems like a very reasonable way of getting a lot more data in the language that you care about versus having no data at all. And why would you not do this if you have access to a translation system? So interestingly, this approach with these big models doesn't actually improve all that much over this zero-shot setting. So here is the table, the same table from before, where you just have the English data. This is over to the left. And then on the right, you have these models that have been fine-tuned on the combination of English text as well as the translated text in whatever language you're looking at. And so if you look down at the bottom models here, you see that the gains are, there are gains, but they're relatively small. So it seems like the multilingual pre-training is doing a great job already. You don't benefit too much from this expensive additional step of adding translations. That said, this is probably something you want to do if your goal is to maximize performance. Okay, and I believe that these numbers have all just been aggregated over all of the different languages. So this is like the average of all of the unseen non-English languages in XNLI. Okay, any questions about?
Do we give any cross-lingual examples in Excel? Like first one is English, second one is German, and then we
No, in this data set, both sentences are in the same language. It would be interesting if the data set was collected in a way that had these kind of like hybrid pairs, but that's also pretty hard to do, because then you need someone who speaks both languages to construct these things.
When we train a model with multiple languages, they probably create a common strategy for tokenization, which works for multiple languages.
Yeah, so we'll talk about this a bit later, but most of these models are using subword tokenization and we talked about the different ways of learning the subword tokenization, like byte pair encoding, for example, is just an algorithm, right? So they applied the byte pair learning algorithm to the concatenation of all the text in all of the languages. So some subwords may only appear in one language, some might appear in multiple different languages. But of course, we saw in byte T5 that they departed from this and used byte level tokenization. Other models have used character level tokenization. I think this is one of the most promising directions for these multilingual models, because you don't have to deal with this case where like one subword means one thing or is used in one way in one language and a different way in a different language, and it's kind of confusing possibly to figure this out with sparsity of data. So yeah, but most models are using subword tokenization, specifically the sentence piece or word piece algorithm.
But even with like same character being used across multiple languages for multiple purposes, so don't that
Yeah, but you'll see way more data per character. So even if it's being used in multiple different languages, because remember in the byte T5 paper, they had a vocabulary of 256. So it's much different than if you have some rare subword that you might have only 1,000 or a few thousand occurrences for each. It's much harder to learn from that.
Have any models been tested using translation at test time? So taking this Swahili or whatever language, translating it into English, and then using like some only English training?
Yeah, we'll talk about this setting or similar setting when we talk about translation. It is a very common thing to do for translation where, let's say I want to translate between language X and language Y, where both of them are low resource, and I don't have any parallel data for X to Y. I can do X to English and then English to Y, and this is using English as a pivot language essentially. So yeah, it's done commonly for translation. We'll look at methods that compare to that in a bit. Yeah. Yeah.
Wouldn't it be more biased with the higher resource languages in our data set? If we start incorrectly those resource languages.
So, I mean, I don't think there's anything specifically about the byte tokenization that would make it biased towards one language. It really depends on how you're sampling the languages in your pre-training procedure. So this is very important as well. If you look at this distribution here, if I'm just randomly sampling documents to pre-train my T5 model on, I'm going to sample way more English documents than I sample whatever these ones down here are, right? So if I want my model to learn a good model of all the languages, I probably want to oversample the languages that are lower resourced and downsample the ones that are higher resourced. And this balance is the subject of many research papers where if you undersample the higher resource languages too much, then your performance drops on basically all languages. But if you don't do anything, then you get very poor performance on low resource languages. So it's kind of tough to balance this. But it's kind of independent of the tokenization. Like regardless of what you do, you need to have some sort of frequency-based language sampling. There have been more complicated things where languages belong to families, right? So two languages could be more related to each other than to another language. So possibly you can do sampling based on language families instead of exact languages. But yeah, we'll talk a little bit more about that. All right, so where were we? Right, so the other of these cross-lingual benchmarks that I wanted to talk about is called tie-dye QA. I thought I had we'll go to their website in a bit, but this task is very similar to Squad. We talked about Squad as this like extractive question answering task. where you have some passage and you're trying to extract the span in that passage that answers the question. So tie-dye QA in addition has yes/no questions, and it also has unanswerable questions that don't have any span associated with it. There are a couple of different tasks in this paper. One, which is different than Squad, is that you're given like an entire article and a question, and you're asked to find which paragraph in this article answers the question. The second task is, given the question and the article, find the span of text in the article that answers the question. So this is much harder. And then there's a third setting, which is the replica of Squad, where you're given the gold passage that has the span, that has an answer in it, and you have to find the span. So this is the one that people commonly evaluate on because it's the easiest one. Okay, so this data set has, I think, 10 or 11 different languages, and they put this table in the paper to kind of contrast the features of all these different languages. So they have languages that are using different scripts. Some languages have white space tokens to denote words, others don't. Most have sentence boundaries. I think only Thai doesn't have it. And there are other features of these languages that differ across different languages. So on their website, I assume this is visible to, okay, yes. On their website, they have some neat examples of interesting phenomena in this data set. So one thing with Arabic and some other languages is that the same entity could be kind of spelled differently in different contexts. So here's one spelling of Mozart in this question context, and then here's another spelling in this other context. So both spellings of Mozart are correct. They refer to the same entity, but they are both acceptable. So here is one issue if you're using, a potential issue if you're using a subword-based tokenizer, right? Because you ideally would want both of these to refer to the same thing, but obviously if you use a subword tokenizer, then these will probably get split up into completely different subwords, right? This MWTS and MWZ. So you really would need to have a lot of occurrences of both of these spellings in order to properly learn that they're referring to the same thing. And with a byte or character level tokenization, you're going to have the same problem that you will still need to see these examples, but probably to a lesser degree. So there's other cases where you have script switching. So sometimes in Russian, you might have the script version of telephone, or it could just be in English, right? This is very common in many languages. You might see text from another language like English interspersed. And the models have to be able to deal with this phenomena as well, because it's very, very common. There are many other types of things that are kind of common to one language or a family of languages that this data set has all of these phenomena. So pretty cool data set. It is probably the case that all or most of the data set was collected by speakers of that language, or at least people who knew that language to some degree if they weren't native speakers. I mean, it's very hard to do this kind of data collection where you have to get experts who can actually write in these languages. If you're using Amazon Mechanical Turk, it's very difficult to do this recruitment process of workers to get in multilingual settings. This work was done by Google, so they have access to a much more powerful annotation force, probably. Anyway, so we can also see the same trend that we saw for XNLI on this data set as well, where here is just the performance if you train on English and you evaluate on one of these other languages. So again, you see this discrepancy from these smaller models. And the categorization is not just the model size, right? It's also the type of data that they were trained on. So MBERT is a smaller model trained on Wikipedia. That was its only source of multilingual data. versus MT5XXL, which is much bigger than MBERT, and it was also trained on much more data from the common crawl. So you can see the impact that both of these features make for the model performance on predicting the right answer in this data set. Okay, so any questions?
Previous slide, this MT5 base, like, does it have the number of parameters?
Oh, that's a good question. I don't actually remember if that's the case.
Because this smaller model is like very good and very simple for home.
Yeah, that's true. But I mean, the data set also differs, so it's hard to tell. Also, T5 again is an encoder-decoder model. So if it had the same number of parameters as BERT, then each of the encoder-decoder would have half the parameters of if they were the same size as the vanilla BERT. So it's very hard to compare when you have these different architectures. But possibly they're controlled for the number of parameters. All right, so let's move on then. One interesting finding that I was kind of alluding to earlier is this, oh, I forgot to repeat the questions. Sorry, I will try and remember from now on. Is this curse of multilinguality, I guess. So this is basically saying that you have one model, it's of a fixed size. As you add more and more languages to this model, the per language capacity decreases, meaning perhaps our performance on a task in that language decreases. And so this is a plot from this paper, which I should have, this is the XLM paper, where it shows the average performance as well as the performance of high resource and low resource languages as a function of the number of languages in this pre-training data set. So you can see here that, and I think this accuracy is either for XNLI or averaged across some multilingual tasks, but you can see that the low resource performance with 7 languages is about 60-something%. The high resource performance is like 80%. And when we go from 7 to 100 languages, the low resource performance goes down, which is interesting because we might hope that adding more and more languages will allow transfer from more and more directions into the particular low resource language. Also, the performance on the high resource languages drops. So both of these things drop, which is obviously undesirable. So there's probably some gap here where I guess if you have a much bigger model, then perhaps this curve would look different. But in any case, as you add more and more data from more and more languages, intuitively it makes sense that at some point it becomes hard for the model to keep track of all of these different sources of information. Okay, there's a question about the zero-shot QA task. What would the performance be like if we just use some translation API and pass that question to the model? I'm not sure, although I will say that the output format for that task is specific to the particular text in the original language. So you would have to translate the passage using Google Translate, apply some English model to get the answer span, and then find the right alignment of that span in English to the passage in the original text to get the answer. So that part might be a little difficult. It's definitely not a trivial thing to do. So I guess you could translate the actual text of the answer in English back, but that also will probably have some issues. So anyway, you could try it and see, I guess. I doubt it performs better than the zero-shot numbers that we looked at earlier. Okay, let me get to the next slide before I answer this next question. Okay, so one way to deal with this problem of as you add more and more languages during pre-training, your performance gets worse, is to add a secondary phase before you fine-tune on your whatever language it is that you care about. You can basically do pre-training on the 100 language common crawl data set that you have, and then do a basically second round of pre-training that is specific to whatever language you're interested in. So for example, let's say I wanted to solve sentiment analysis in, I don't know, what's Korean. So I'm going to train my model on 100 different languages. Then I'm just going to continue pre-training, but I'm only going to do Korean. So here the model is kind of specialized to Korean, but if we do this for too long, then the model will probably forget a lot of the stuff it learned from the other languages. So there's probably some middle ground in which we want to stop this second pre-training phase. And one of the, and so that is this catastrophic forgetting problem, right? If we keep pre-training in Korean, then we probably will forget everything else. So one thing that has been proposed recently is to just train a very small number of parameters during the secondary phase that's language specific. So we're not going to get too much into the details of this. This is one of the assigned papers, this MADX paper. Basically, in each transformer block, they just add like a single small layer, which is specific to a particular language. And so if I'm doing this secondary pre-training in Korean, I'm only going to backpropagate and update these small language-specific parameters. So I learned some Korean module essentially in the network. But if I wanted to do any other language, I would just swap out this Korean adapter module for a different language adapter module. So these adapter things are kind of very similar to the prompts that we saw in previous work. And nowadays there are people working on prompt-based learning in multilingual scenarios, which is also going to be very interesting if that works. So the idea here, of course, is that to avoid catastrophic forgetting, we're going to freeze the vast majority of our parameters to whatever has been learned during the multilingual pre-training phase. And we're only going to update a very small number of parameters. So these could be learned from scratch, for example, for Korean. That way, most of the knowledge is still encoded in the frozen parameters. All right. Yeah, good statement here. All right, let me answer this question. How do we deal with the credit assignment problem when we are scoring the accuracy of a given translation that has been generated with a model using the causal LM? I'm not sure what you mean by the credit assignment problem here. Maybe you can clarify. I will just move on. So let's shift gears now. We've been talking about these, XNLI, tie-dye QA, these multilingual tasks, but probably the most prominent multilingual task is machine translation. And there's been a lot of cool work recently on improving machine translation, allowing for a single model and many-to-many translation. So, there's a lot of effort in the past 2 decades on collecting large-scale parallel data sets. So a parallel corpus is one where you have a sentence in English and it's paired with a translation of that sentence in some other language. Sorry, it doesn't have to be English, right? I just said that because most of these data sets have English as one of the sides. And this table shows all of these English to X data sets. These aren't like the largest numbers, but they give you some idea of the limitations that we have here. If you have to use translations that are produced by humans, it's going to be hard for you to collect billions and billions of pairs of data, right? And so there's been a lot of work on trying to transfer the knowledge that you learned from, say, a Romanian English translation system to a Bulgarian English, or that was just an example. But there's no reason why, if I wanted to translate Romanian to English, I have to use a model that can only do that translation direction and has learned nothing from any other language pair. And so a couple of years ago, we had a lot of papers on something called unsupervised machine translation, which is, really cool. The idea, for any of you who have seen the movie Arrival, it's kind of like similar to that. Okay, what is this comment? Me being a beginner in NLP, trying to look cool by acting that I'm understanding. Okay, well, I guess if you watch all the videos, then you could actually understand stuff. But thanks for the comment. Okay, so right, getting back to this. In unsupervised machine translation, the idea is that, let's say I want to translate from language A to language B. I have no parallel data between language A and language B, meaning I have no human written translations. I only have text in language A and text in language B. So for those of you who have seen Arrival, we obviously wanted to translate between the alien language and English, but we had English data, but we had no alien data as well. So we had like very extremely low resource data for the alien language. I would highly recommend anyone who hasn't seen that movie to watch it. But in this case, we have a more reasonable assumption where we have a lot of monolingual data in each language. And the way that this generally works is you have a word embedding model that you train in each language. So for example, I can train a word embedding model in English, a word embedding model in French, and I can align the two vector spaces together. So I can find, and this is probably the most interesting thing about this line of work, is that the vector space of these word embeddings looks similar regardless of what language they are. So like the position of cat in this vector space and cat, the French translation in the French vector space, are close together. So you can actually have a mapping, learn a mapping between words without having any sort of parallel data between the two languages. I mean, it probably helps that in French or some other language, there'll be some English words that allow you to ground the meaning of some word in both of the languages. So in some sense, you have some signal from some parallel signal. But anyway, we're not going to talk more about this line of work because even though you could get like reasonable quality MT systems, they were still very, very far away from the state of the art. And in particular, they were also underperforming systems where you might just collect 100 parallel sentences and then you would get a much better system than one of these fancy unsupervised ones. So in most settings, it's very practical for you to collect like 100 sentences in this language direction and train a model. So why do you need to use all this fancy stuff when you have zero parallel data? It's only the case where the parallel data is completely unfeasible to obtain, like in the case of like alien translation. But one of the features of these unsupervised systems was this idea of back translation. So we will talk about this because it's useful not only for translation, but for a variety of different other tasks. And so back translation was first proposed for this setting where you have a very small parallel data set. So maybe you have like 100 pairs between language A and language B, sentence pairs. But you have a lot of data in both of these languages that are unpaired. So you might have the common crawl subset for language A and for language B. So the idea here is that, and here in this example, we're doing English to French. So we have a small number of parallel English to French examples, a large number of French monolingual examples. The first thing we do is train our English to French model on, we train the English to French model on our very small parallel data set of just 100 examples. So this was before the kind of pre-training became very popular. So we were training this model from scratch. You can imagine like a sequence to sequence model trained from scratch on a very small number of parallel pairs. It's not going to be good, right? But it will probably learn something. So then you take this model, which is not good, and you use it to translate the monolingual data that you have, this French data, into English. So you can learn both sides of this translation, right? English to French. You can learn French to English. You have the same data used for that. You just flip which side you're doing. So if I go English to French, then I take my monolingual data, translate it using my bad model that I just learned into English. And now I have pseudo-parallel data, right? I've created this like noisy version of these translations using my bad translation model. But the idea is that there's some signal present in this noise that I can use to improve the base model that I initially used. And so you can see how this process can progress in rounds, right? I could use my initial model to get some initial noisy English data, retrain or fine-tune my translation model on the concatenation of the real data and all of this pseudo-parallel data. Now I have a new translation system. Maybe it's a little better. So I'm going to retranslate my monolingual data, do this whole thing again and again, and maybe I get a better model. So that's the general idea of back translation. But it's also a good way of getting paraphrase data. So let's say I don't care about translation. And let's say I just have a translation model from English to French and French to English. So if I wanted to get a paraphrase of some English sentence, I could feed in that sentence to my English to French model. So now I have a French translation. I'm going to feed that translation back to a French to English model. So now I get an English output. And through this process of translating 2 times, I've introduced some kind of noise. It's kind of structured noise. These translation models make the same kinds of reorderings or whatever when they're doing translation. And so the English sentence that I end up with here is likely going to look different than the one that was input first. And it might be different syntactically, or some words might have been replaced with synonyms. You know, all this noise that can happen in translation. And ideally, I would be able to use this to get a large data set of paraphrases. Yeah.
Does this work if you use Google Translate? Or because I feel like in Google Translate, if you hit the like switch button, then it'll actually go back to the original.
Yeah, so this does work in Google Translate. The extra credit homework that we will release soon has part of it is using Google Translate to do back translation for basically paraphrase generation. So yeah, it works. One thing that you need to keep in mind is the choice of language that you're translating to. So if you translate into a very different language than the source language, it's likely that you'll get a lot more diversity in your outputs because, or you know, a language where the machine translation system isn't very good, you'll get diversity, but probably at the expense of maintaining the semantics of your input. This is also a very useful strategy for data augmentation. So if you have you know, limited data set in whatever task you want, you can use back translation to get a bunch of paraphrases of your original data set that you can use to train your model. Yeah.
It seems like a lot of like experience setting that we translate it to the translate the text to English, and then we can translate it back to the French, and then check how similar these 2 translations are, and then we can train these 2.
Oh, you mean if you had a model that can predict if this is a translation or not, or?
Yeah, some experience setting based on this back translation.
Yeah, I mean, in theory, yes. In practice, it's very hard to apply those signals because remember, again, that the output of the translation system is like a discrete series of decisions made during the beam search or sampling process, right? So you only have one output. You have all of these issues with this discrete output versus like in images, it's very easy to do this because you have just continuous outputs. So, oh, I forgot to repeat your question, but the question was, can we use this kind of setup to train like an adversarial GAN-like model for text? So people have tried. I think it doesn't work really because it's hard to use that signal at the sequence level. Yeah.
In the cross-lingual zero-shot learning, are we having parallel data where we're training on multiple languages, or is it totally independent data?
Yeah, so the question is, in the cross-lingual zero-shot transfer setting, do we have parallel data between, like, every example is occurs in English and French and all these other languages? No, we don't. So the setup is just you have data in each of these languages, they're independent, and you're generally, in the zero-shot case, holding out all of the other language data, just training on, say, English and testing on the other languages. So it's, a very difficult setting. Yeah.
So if you use the back translation like on a low resource language, then how does it, are there like experiments conducted on that? How does it compare to like other like?
Yeah. So this is these are the results from the original back translation paper in 2016. So you can see that for English to German, if you use only the parallel data, and German is actually a pretty high resource language, so you have a lot of parallel data here, you get a blue score. So we learned about blue score. Here's a case where it's actually being used, of 20.4. And if you add this back translation process to this thing, you get an improvement of about 3 blue points, which is very large, actually. So in general, an improvement of 1 blue point is a significant improvement. 3 blue points is a lot. And you can see this also in this other data set. I think this is a different domain, still English to German. You get a similar improvement of about 3 blue score when you do this. So your question, though, is how does this compare to more recent models that might take advantage of pre-training or other things like that? If you read the paper for today, the ManytoMany translation, they were still using back translation in that setup, and I think it gave some smaller gains. It's definitely not on the order of 3 blue points, but it's still used in today's systems as well. Yeah.
When you like that translation, meaning that getting the police parallel data as well as getting using the super parallel.
Yeah.
Data.
Yeah.
We have to train this again and again, right? Progressively.
I'm not sure if they did the iterative thing or just one pass through it. I forget what happened, but okay. There's a lot of these YouTube questions. Let's see. So Budgie has posted some clarifications. Aren't we generating text token by token? We have a generated sentence and may compute the blue score. How do we commute? Oh, I see. So this question is related to your question about can we use this in the adversarial setup. I think this question implies that the goal is to use the blue score as a signal to further improve the model. So for example, if I do beam search, I produce a translation and it has a very low blue score, can I use this as feedback to the model so next time it produces something with a higher blue score? I think many of you have asked similar questions. In this kind of setup, you generally have to use reinforcement learning to backpropagate that reward back through the decoding process. Because remember that when you produce a translation, this is a sequence of decisions where at each step you're choosing one token out of your entire vocabulary to produce. And beam search and greedy search and all of these things, they're not, they're approximate search algorithms. You might find something that has the highest probability. You might have something that has low probability, right? So you get only one sample from the model when you apply one of these decoding algorithms out of a space of possibly many translations that have high probability. So it's very hard to take like just one sample from this model, which is actually a sequence of these independent or these individual decisions. You only get the reward signal, the blue score, at the end of this process when you produce the end of sequence token. So this is where the credit assignment problem that Budgie mentions comes into play, where if you get the reward at the sequence level, you don't know which decision you made contributed most to the low blue score of this particular translation. So there have been a lot of papers on using reinforcement learning for this process. We at my group and Andrew McCallum's group had a paper on using energy-based models to do this, but I think all of the methods are pretty cool, but the conclusion is they don't really work too well. And also, some interesting results from these reinforcement learning-based methods are that you can use it to improve the blue score, but it doesn't actually improve the quality of the translations when a human reads them. So it's kind of like gaming the blue score by sometimes, messing with how punctuation is produced, or these other very low-level things that can boost your BLEU score up a little, but if a human looks at it, they won't be able to distinguish any improvement in the. So we have a long way to go before we can actually learn from these sequence level rewards. All right. The source language may contain words of a third language or target language. Indians use English words in between their regular conversations. How can an NMT model resolve this? Can it translate if the source sentence contains English words? Yeah, so this is a good question. Again, this is something that depends on tokenization, right? So if you have, so before we had these like pre-training and different tokenizations and stuff, you would have a separate vocabulary for your source language, a separate vocabulary for your target language. You would have an encoder-decoder model structure, and the decoder could only produce whatever you have determined to be words in the target language. So if you didn't see enough occurrences of these English words that were in your target language, they wouldn't have been in the vocabulary. They would be converted to unknown tokens or something like that. Then later on, people developed this notion of maybe copy mechanisms would be useful. If I see an English word in the source sentence, I could be able to copy it over even if I'm generating text in a target language. But nowadays, with a byte level model, it's kind of irrelevant, right? The model should be able to learn from these examples that, oh, well, in this case, I'm producing text from a different language, but I saw it already in this language, so there's no separate vocabulary here. I think these days this is probably less of an issue, but obviously all of these models that we're talking about were released in like 2021, so it's hard to say if they actually solve these issues and don't require any special modification of the model. All right, let's move on. So the last thing I wanted to talk about today is this many-to-many translation, which was the main reading for today. I think it's super cool. So essentially, the idea is to have a single model capable of translating between any of 100 languages to any of another language in that setup. And so this paper actually goes beyond the standard approach of many-to-many translation, which is there's a lot of data to or from English, so language X to English. And many people use this kind of data to train these many-to-many systems by using English as a pivot language, as I described before. But we can probably do better if we have, what if we have data from another language pair, or we mine data from another language pair, like language X to language Y. We can also use this to further improve the quality of our system, and maybe we don't have to resort to having this pivot language anymore. The problem with having a pivot language is now you're doing 2 steps of translation. There's 2 potential sources of noise instead of just one. We'd like it to be seamless, all done in one model if possible. So this paper had a lot of space devoted to the data gathering, which was cool. They selected 100 languages that had some criteria. So they wanted to have geographic diversity, and they did they chose languages based on what families they belong to, have diverse families as well. They needed to have at least some parallel data from like language X to any other language in each of these languages, and this is for evaluation purposes. So if I include some language in my data set, I want to know how well I did in translating to that data set, right? So I need some evaluation data. So even if it was a small amount, they needed to have some. And of course, they need to have monolingual data available. And this could be much larger. It could be from the Common Crawl or whatever. So what they did, the main source of their data was taking existing bilingual data sets, like for example, English to French, English to German, all of these data sets that have been collected in the past, and just merging them into a single data set. So they take all of these parallel corpora, and in addition to that, they mine additional parallel data from just the web. So this part of their paper was pretty interesting. We won't get into it in too much detail, but essentially they took sentences from language A. They encoded each sentence using some multilingual sentence encoder. And then they just searched across like a huge data set of encoded sentences from a bunch of different languages to see if they found any sentences that were similar to that particular sentence, but in a different language. And then after some filtering, they were able to find almost exact translations, even though these are not like translated by humans. They might be sentences written by one person in one language that happen to be a translation of the sentence written in another language. And so you can mine data in this way. Maybe it's a little noisier than human translation data, but it's still very useful, even if it's approximately the same meaning. So anyway, they get all this data, and they concatenate it all together and apply the sentence piece tokenization, which is one of the subword tokenization methods that we learned about, similar to BPE, except using something other than frequency to do these merge operations. So in the end, after all of this, they have 7.5 billion parallel sentences. So it's a pretty big data set. And these data are in 2,200 different directions. So language A to language B. And yeah, they use back translation to further augment their data to get even more than the 7.5 billion here. Yeah.
They try to like limit how much each language has in those like separate.
Yeah. So in their paper, they talk about sampling approaches to downsample common language pairs, upsample. It's the same as in the like MT5 kind of, if you're training a language model. I forget how similar the two approaches are, but you can check it out in the paper. Okay, so their results were pretty interesting because before this, I'm not sure if this was the first paper to show that many-to-many translation is actually working better than other systems, but before this, there had been a lot of attempts at many-to-many translation. So many-to-many means you have one model that can translate in arbitrary directions. But those models had all been worse than just training on language A to language B's parallel data and ignoring all the other language data. So these are the bilingual baselines here. And so they had in this table their results. These are the blue scores with a couple baseline models. So in their bilingual baseline, if they have a specific source language and target language, they train their model only using the source and target language. I don't think they did any pre-training here or anything like that, so they're training from scratch. In the English-centric version, their training data is bigger than the bilingual data. So here, they're including all directions involving either language X or language Y that also involve English. It's like English to any language and any language to English. All of these data sets are included in this training data set. But at test time, they try to translate from language X to language Y. So there's no English used at test time. So this system is kind of weak because the test time usage is different than the training time. At training time, you always have English in one side. At test time, you have like two potentially low resource settings. And finally, we have the English-centric with pivot, which is what I mentioned in my response to you, where you actually do the translation into English or from English to X. Sorry, yeah, you do the translation into English, then you do English to the other language. So you're doing two separate phases here. And if you look at the results, this is the average of all of these 100 languages to English, the average blue score. You see that the bilingual baselines are actually doing significantly worse than the many-to-many baseline, which means that this is actually allowing the model to transfer knowledge from these other language pairs to the particular pair that's being evaluated. It's also slightly better than the English-centric way. So in the English-centric way, we have the mismatch again at train and test time. From English, the bilingual baseline is actually a little bit better here. So if we have English to X, then this many-to-many translation system doesn't seem to be helping. But the real gains are observed in non-English. So neither side is English. In this case, we get huge gains from the many-to-many translation model. you can see that the bilingual baseline is bad. Why is it bad? Because it's trained on probably a very small amount of data from language X to language Y, where neither of them are English. The English-centric model is even worse. This makes sense because here, the English-centric model has seen English as one of its directions, so it makes sense that it's good at both of these tasks. But if neither language is English, then this model is out of distribution. The pivot-based approach is a little bit better, but this many-to-many system is much better. So this is a big win for this kind of transfer learning between languages. Yeah.
Is this all evaluating like the same model trained different ways, or are they different models?
Yeah, I think these are all the same architecture trained in different ways. I mean, it's hard to do this with varying the number of examples that you have, but that's probably the fairest way to do this comparison. Yeah. And their model is just a transformer encoder, transformer decoder, nothing fancy. Yeah.
Why doesn't course of multilinguality play a role here? Because we are feeding too many languages in ManytoMany. Why does it improve the performance instead of increasing it in all the languages?
Well, it's unclear if we've hit that. That plot was only for a particular model size and data set. Here, the task is different. It's translation. And the model size is much bigger. This is like a 1.2 or 3 billion parameter model. It might get even better as you scale, but yeah. I mean, also in this case, like not all language pairs are observed in the data, so there's room to expand that data set even more to more and more language pairs, directions, I mean, of parallel data. So remember, this model is trained entirely on parallel data as well. So I think the whole setup is a little different than in the language modeling case. Yeah.
Could it be that the performance of these baselines is better, especially English-centric, is better for one specific family which is closer to English?
So, I forgot to repeat questions. Okay, yeah, the question is, could it be that one of these baselines is better on a certain family than the many-to-many model and maybe worse on other families? Yeah, I'm sure all of that results broken down by that are in the paper. I haven't looked in detail, but you should check it out and see. Okay, so another thing that's cool is zero-shot performance. I should mention that how this works is that it's just a vanilla transformer encoder decoder architecture. There's one unique thing about this where on the encoder side, there's a special token that says what language the input is in. And on the decoder side, there's a special token that corresponds to the identity of the target language. So to change what language you're translating into, you would just feed in a different language token at test time. So to do this, if you have this set up, then you can also do zero-shot translation, right? So you can look at languages for which you have parallel data, like through their data collection process, and languages where you have no language pairs where you have no parallel data at all. So that's what they did in this experiment. So with the bytext means that, wait. I wonder why this is higher than, okay, maybe I misunderstood this table. All right, I will have to read more about this and before I say anything about it, because I thought it meant one thing, but maybe it's a different. Anyway, this model is capable of zero-shot translation. I'm not going to say more than that. So another experiment that they do in this work is, so here there were no language-specific parameters other than that one token that indicated the identity of the language in the encoder and decoder. They tried to add some language-specific parameters, like a whole layer that is unique to each language, and you can swap those out. They did some stuff with language families as well, and they found small improvements by having not just a single token identifying language, but also having a small set of parameters tuned for a particular language. So this is again in the vein of keeping most of your model frozen, adding a very small number of language-specific parameters. You can see the operation here, right? Here you have some Chinese input. This is the special token indicating that this is a Chinese, and you feed it to the encoder. Then in your decoder, you have this special token indicating you want to produce French. And this decoder, you might have some specific parameters that are specific to a language group that the model will then use before producing the final translation. So this is like, this part is a language-specific parameter part. But they also tried without this part where you just have this French token inserted and the model produces the translation. Okay, so I wanted to just conclude with the results here. They evaluated over a ton of different directions from this WMT, Workshop of Machine Translation, shared tasks over the past few years. They found that these 4 directions they were not able to improve on with their many-to-many system, but all of these pairs they were able to have some improvements on, and some of these improvements are actually quite huge. So Turkish to English, they were able to get a almost 8-point blue improvement. Chinese seems, it has always been one of the hardest languages to translate into, and unfortunately this was not able to, it actually got worse results than the bilingual baseline. So a lot of work to be done there, but overall this is very promising. Okay, so I think any final questions? Maybe I'll go over the quizzes next time. Yeah.
Was that special token idea used by other papers, or was that like a new idea that they had?
I don't think it's a new idea. I can't think of a paper that used it before them, but I'm sure, I think, so there was a paper by Google, I remember, like one-to-many translation, where they also used a special token in the decoder to describe what language to generate into. But yeah, it's a pretty common thing. All right, see you all next time then.